Hey everyone, in this video, we're going to look at example 2 in our section 6.2 of our workbook. So example 2 is very similar to example 1. The goal is to compute an area that's created by rotating curves around an axis. So let's go ahead and set up the picture first, and then understand what the volume looks like and how to break up the volume to compute the total volume. All right, so we're told to find the volume of the solid region generated by rotating the region bounded by y equals 2, x equals 0, and y equals cubed root of x about the x-axis. So the first step that we're going to do is to just draw out these three curves to get an idea of what that region that we're rotating looks like. All right, so I'm going to set up my axes here. Okay, so y equals 2. So if I draw 1, 2, I'm just going to label my axes, my y-axis here, x here. So y equals 2 will just be the line, the horizontal line at y equals 2. X equals 0 is just the vertical function. Maybe I'll use red so we can really tell the difference here. So here is y equals 2. X equals 0 is just a vertical line at x equals 0. And then finally, y equals cubed root of x. We can go ahead and write up that function on a graphing calculator or a graphing program online. And we see that that function looks a little bit steeper than the square root. Okay, cool. So now we can start to see the region bounded by these three curves. Region bounded by these curves. And we're going to rotate that region about the x-axis. So what would that look like? So that means we're going to fix this x-axis and rotate everything. So what happens here is that then we'd have a symmetric view down here. I'm going to continue my graph. At y equals -2 is where that top line will cross, or be. This line will rotate down like this. And the shape that we get will look something like this. It'll come out of the page. Make slices like this. Notice, though, that these slices will have a little bit of volume taken out of the inside, too. All right. So it'll almost look like a cylinder if we rotate our heads. Cylinder like this. Almost look like a cylinder like this, but we will have scraped out some of the cylinder with like a cone type of object. Okay. So now that we have a sense of what the shape is going to look like, we want to get a better idea of some of the parameters here. So we see that this object starts at 0 on the x-axis, but what does it go to? How high does this cylinder go, or volume go? Well, it goes to as high as these two graphs, y equals 2 and y equals cubed root of x. It goes to where they intersect. So it's that x value where they intersect. So how are we going to find that value? Well, how we find it is to set those two functions equal. So we want to know what x makes the cubed root of x equal to 2. Because we're setting y equal to 2. So we need to solve this equation for x. So how do we do that? Well, we need to get the x out of that cube root. So I'm going to cube both sides. So now I get x equals 2 cubed. 2 cubed is 8. So that means where those two graphs intersect is at 8. Okay. So now that we've drawn our volume, we want to get a sense of the types of shapes that we're going to add up together, or the type of shape and its volume that we need to add up. And so as we sort of drew here to suggest, we're going to have these slices again. But now, rather than this disk that we saw in the previous problem, we're going to have a hole cut out of our disk. So let's go ahead and see what that looks like. And we can even, while we're at it, compute the volume of a disk. All right, so what does it look like? Well, we have a outer circle, and then it's cut out in the middle. And it's going, we see these all are stringed along the x-axis. So that can help us make sense of the geometries on our little washers. Okay. So as we see here, we're going to have two different radii that we want to consider. One, I'm going to change colors here so we can really see it, is the radius of the smaller circle that we're cut out. So let's call that R1. Then the second radius is the radius of the outer circle, so R2. Okay, so what are those? Well, we see that R1 ends at our function here, given by y equals cubed root of x. And our outer radius ends here at the function y equals 2. So that means our inner radius is going to be given by cubed root of x. And our outer radius will be given by just 2. So what will the volume be? Well, the volume is similar to how we computed the volume of the disk from before, but now we need to remove that inner disk as well, because we only want this kind of donut-y shape. So the thickness of our disk is still change of x, or dx, or delta x. Kind of trying to draw 3D here. So our thickness is still going to be dx. And now to compute the volume, we need the area of the yellow part that we shaded over. So that area is going to be pi r squared, so the area of the larger part, minus the area inside that we want to remove. So minus pi cube root of x squared. And then to that, we need to multiply by dx, the little change of x. Okay, so now we have the volume of one disk set up. So now we need to compute the entire volume. So to do that, again, we're going to use an integral. We already saw that we're only looking at x starting from 0 and going up to 8. So our bounds here are 0 to 8. And what are we adding up? Well, we're going to add up the volumes of each of these disks. So pi 2 squared minus pi cube root of x squared dx. Okay, so let's go ahead and clean up this integral a little bit. So we see that we get the integral from 0 to 8. 2 squared is just 4. So we get 4 pi minus pi. And then I'm going to combine this square and cubed just to make a fractional exponent. So that would be x to the 2 over 3 dx. All right, so now this integral should look fairly doable for us. We just have a constant here and an x with an exponent here. So the antiderivative becomes 4 pi x minus pi, that constant I can just bring out, x to the power of 5/3. And that is, I'm just going to add, I'm adding 1 to my exponent. So 2/3 plus 1, that's adding 3 over 3, which is 5/3. Okay. Feel free to use your margins or scratch paper for any of that additional work. And then we just need to remember that we need to divide by that 5 over 3. In other words, multiply by 3 over 5. I'm going to stick that out front, 3 over 5. And then we're going to evaluate this at 0 and 8. All right, I'm going to clean up my paper a little bit just so we have some room to continue this integral. All right, so when we do that and we plug in 8, we get 4 pi times 8 minus pi times 3 over 5 times 8 minus, then we're going to plug in at 0. But notice when we plug in at 0, both terms go away. So we just get a minus 0. All right. And now when we combine that, we can see that we can factor out a pi from both sides. And when we compute that difference, we get 64 over 5 pi. So the volume here of this shape is 65. Oops, I said it, but I didn't write it correct. 64. We should be getting 64 over 5. So our volume is 64 over 5 pi. All right, nice work going through this example. Please feel free to rewatch this video, go over it again, maybe do it on your own. Make sure you're feeling really comfortable with the method that we're looking at here.